Okay, welcome to the first segment of an introduction to information theory. In the last segment, we introduced Shannon Entropy. It basically computes the amount of information in a message. Alternatively, we can think of that as the minimum number of bits needed to represent the message. And it's given by the expression here. One way to interpret this expression is basically the Shannon entropy is just the average amount of information over all outcomes. So for each outcome, let's say outcome X, the amount of information we obtain from that outcome X will be just minus log Px if that outcome actually happens. So it's actually quite intuitive because we think of that when the probability of an outcome is smaller, so that's basically the outcome is not likely to happen, then the amount of information we obtain when the outcome actually happens will be bigger, so a rare event contains more information. So anyway, we'll give more evidence why the Shannon entropy is given by this expression later on, but for now I just want to look into a simple example here. So let's say we have a random variable x is represents the outcome from flipping an unbiased count. Let's calculate the Shannon entropy hx. And so since x is unbiased, we have ph is equal to pt equal to 0.5. Let's just substitute into pH and PT into this expression here. So we have hx is equal to sum over. So note that we are actually summing over the outcomes. So the outcomes here is head and tail. So therefore we have minus p head log p head minus p tail log p tail. And by the way, we are using log to represent log base 2 here. And for all these videos, basically, unless we specify in particular, we are using log base 2 all the time. And the unit for the Shannon entropy will be bits if we use log base 2. And so log base 2 of 0.5 will be minus 1. And this is 0.5. 0.5 minus 1. So basically it's 0.5 plus 0.5 is equal to 1 bit. And it's exactly what we expected. So it's pretty nice. So how about if we have the count is actually biased? So let's say if p hat is equal to 0.1 and p tail is equal to 0.1. Again, we can just substitute into this equation, and it turns out that hx will be approximately 0.47. So so this is 0.9 here. Actually, the amount of information of the outcome of flipping a biased count will be smaller than flipping an unbiased count from the Shannon entropy expression. So let's look at the extreme case. Let's say if we always get a tail, in the sense that we have p tail is equal to 1 and p head is equal to 0. So the count is basically so biased that we always get a tail. I don't know how you can do that, but let's say if we have a count as biased as this, and then if we substitute pH and p tail into the expression hx there, we have minus 0 log 0 minus 1 log 1. And of course log 1 is just equal to 0, therefore the second term is just equal to 0. The first term is a little bit tricky, but we can compute that by taking the limit. Let's say we have to take a limit a equal to 0, compute a log a. for a goes to 0, and this will be equal to log a over a, 1 over a, and a go to 0. Now we can use the L'Hopital's rule, basically taking derivative above and below. I mean, both the denominator and numerator won't change the limit, so that will give us log a will be basically some constant over a, and this will give us 1 minus 1 over a squared. And if we take this will be basically the constant times a. So if we take the limit that a go to 0, it will just give us 0. So okay, therefore like hx would be just equal to 0 here. And of course this is obvious because when the variable is actually deterministic, then if I need to convey to another party that what is the outcome, in this case the other party basically will know that the outcome will be always tail anyway, so I don't really need to send her anything to let her know that the outcome is tail.